Assalamualaikum. In this video presentation, we will be discussing on Planck's hypothesis. My name is Muhammad Ashrik bin Suib and
My name is Nur Farah Fahna binti Ahmad Nasri. We are from group AS2513D2. We'll summarize about Planck hypothesis. This is the Max Planck, where he introduced the concept of quantum of action. In 1918, he was awarded the Nobel Prize for discovery of the quantized nature of energy. Wien's exponential law, and N energy density is proportional to the temperature. This rearranged equation shows why the peak wavelength decreases as temperature increases. This decrease in wavelength explains why objects glow first red, then orange red, then yellow, then even blue. These colors are successive decrease in wavelength. Rayleigh-Jean's equation is consider the cavity as it emits blackbody radiation. The power emitted from the blackbody is proportional to the radiation energy density in the cavity. This is the formula for Rayleigh-Jean's equation, where the value for this one is referred to the average energy per mole according to the kinetic theory. Meanwhile, this value is referred to the mode in cavity in range d lambda. At a long wavelength, the law matches experimental result very well. At a short wavelength, there was a major disagreement between the Rayleigh-Jean law and experiment. This mixed match became known as the ultraviolet spectroscopy, where infinite energy as the wavelength approached zero. This is the draft intensity versus wavelength, where the red one is referred to the classical theory. Meanwhile, in the blue one is referred to the experimental data. We can see at this one shows that classical theory intensity is growing without bound for short wavelength. This is the formula for Stephen-Boltzmann law, where P is power radiated, S is the Stephen's constant, A is surface area, and T is for temperature of body in unit of Kelvin. Therefore, the power radiated is proportional to the T to the power of 4 for an identical body, which explains why the area under the blackbody curve increased so much for a relatively small increase in temperature. In 1900, Planck developed a theory of blackbody radiation that leads to an equation for the intensity of the radiation. This equation is in complete agreement with experimental observation. He assumed the cavity radiation comes from atomic oscillation in the cavity walls. Planck made two assumptions about the nature of the oscillators in the cavity walls. For the Planck assumption, we will proceed to Muhammad Nasri. Thank you.
thank you Nur Farah Fahana. Next is on Planck's assumption. Planck have made two assumptions, where the first assumption is that the electromagnetic radiation by the blackbody is discrete, or in another word, separate packets of energy known as quanta. This means that the energy of electromagnetic radiation is quantized. The second assumption is that the energy size of the radiation depends on its frequency. Planck postulated that the energies could take discrete values equal to multiples of a fundamental energy. As you can see in this formula, where n is a positive integer called the quantum number, f is the frequency of the oscillation, and h is the Planck's constant. The average energy of a wave is the average energy difference between levels of the oscillator, weight according to the probability of the wave being emitted. This weighing is described by the Boltzmann distribution law and gives the probability of being occupied as being proportional to this formula, where E is the energy of the state. As you can see here, this is the graph of the Planck's model. At the top of this graph is somewhere between very short and very long wavelengths. the product of increasing probability of transition and decreasing energy per transition result in a maximum in the intensity. As the wavelength increase, there is a small separation between energy levels, leading to a high probability of excited states and many downward transitions. The low energy in each transition leads to low intensity. At a shorter wavelength, there is a larger separation between energy levels, leading to a low probability of excited states and few downward transitions. The low probability of transition leads to low intensity. This is the Planck's distribution formula. As you can see, h, as I said before, is the Planck constant, c is the speed of light, p is the power per area per meter wavelength, k is the constant, and T is temperature in Kelvin. In the Planck's quantum, the energy of electromagnetic radiation is quantized, whereas in the classical theory, energy of the electromagnetic radiation is continuously. As well as in the Planck's quantum, energy of electromagnetic radiation depends on its frequency of wavelength, while in the classical theory, the energy of electromagnetic radiation does not depend on its frequency or wavelength. Here is the Einstein's and Planck's result. Einstein derived Planck's results by assuming the oscillation of the electromagnetic field were themselves quantized. In other words, Einstein proposed that quantization is a fundamental property of light and other electromagnetic radiation. This led to the concept of photons. And that is all for our discussion on Planck's hypothesis. Hopefully this video will be useful, and thank you.